Here we go, start another chapter. This time let's take a look at chapter 7. Okay, chapter 7 talks about naming polygons. So we had three-sided figures we called triangles. We had 7 different types of triangles, like right triangles and equilateral triangles, acute triangles, and so on. We talked about our 4-sided figures, which were our quadrilaterals, our rectangles, and our trapezoids, and our kites, and all of that. Now we need to talk about what happens when it has 5 sides, or 6 sides, or 7 sides, 8 sides, 9 sides, even 10 sides. Okay, so take a look. 5-sided figure is called a pentagon, 6-side, hexagon, 7 sides, heptagon, 8 sides, octagon, 9 sides, nonagon, 10 sides, decagon. Okay, if you need to, take a minute, pause the video right now, copy this down into your notes. Okay, I'm going to assume that we're good. I'm going to assume that most of us have probably seen these words before, maybe the heptagon, maybe not, but most of us have seen these words before. But here's my next question. What happens if it has more than 10 sides? What happens if it goes beyond this point right there? Okay, so while there are names for everything past 10, I'm not asking you to learn them. Okay, they mostly have Latin roots put together. But I'm not worried about that. Anything past 10, we take the number, we put a dash, we put the word gone. So 25 sides, 25 gone. 87 sides, 87 gone. Okay? I'm asking you to learn the names from 3 through 10, and after that, we just call it a whatever number gone. Okay, so it's time to talk about some formulas. Okay, I'm going to help you derive the formula for the sum of the interior angles of a polygon. So here's what we know. Okay? We know if the figure has 3 sides, it's called a triangle. The sum of those 3 angles in a triangle is 180. We saw in our quadrilateral chapter that the angles in a quadrilateral, whether it's a parallelogram or trapezoid, doesn't matter. The sum of the angles is 360. But we didn't talk about y. Okay, so let's explore y. So if I draw a diagonal in any one of my quadrilaterals, I will split the quadrilateral into 2 triangles. Okay, maybe in your head you want to see that. Okay, take a trapezoid, put in a diagonal, you get 2 triangles. Okay, take a look at a kite, put a diagonal in, you get 2 triangles. So every quadrilateral, when you put in a diagonal, it splits into 2 different triangles. Each triangle has a sum of 180, therefore I've got a sum of 360. Okay, next take a look at any kind of pentagon you can draw. So 1, 2, 3, 4, 5 sides, that makes it a pentagon. Okay, if I take one point, so I'm going to take this point right here, one vertex, and I draw in all the diagonals from that vertex, okay, it looks something like this. I can draw one diagonal right there and a second diagonal right there. So what did I just do? I just split it up into 3 triangles. Well, there's 180, there's 180, and there's 180. So if the sum of those 3 is 180, 3 times 180, I'm getting a total sum of 540. Okay, not my finest looking hexagon, but 1, 2, 3, 4, 5, 6 sides makes that a hexagon. Again, if I pick one vertex, so I'm going to pick this top one, and I draw in as many diagonals as I can from that vertex, let's see what happens. Okay, from that vertex, I can draw 1, 2, I can now draw 3 diagonals, which leave me with 1, 2, 3, 4 triangles. If the sum of the angles in each triangle is 180 degrees, I now get a total sum of 720. So maybe you're seeing a pattern between these numbers, maybe you're not. Maybe you're seeing that, hey look, I went from 1 triangle to 2 triangles to 3 triangles to 4 triangles. But what if I asked you to find the sum of the interior angles for something that has 22 sides? I don't want to have to try to figure out, is it 1, 2, 3, 4? That's a lot of triangles. So we need to have a formula here. We need to have a way to speed this up. Okay, so I took away the pictures and now look at what I've written. So if it is a triangle, we know the sum is 180 degrees. Quadrilateral, 360. Okay, but the 360 we said came from splitting it into 2 triangles. The 540 from splitting it into 3 triangles. The 720 from splitting it into 4 triangles. So we need to make a connection between these numbers, 1, 2, 3, and 4, and these numbers, 3, 4, 5, and 6. Okay, if I look for the connection, I will see that this number over here is always 2 less than the number of sides. Okay, 3 minus 2 gets me 1. 4 minus 2 gets me 2. 5 minus 2 gets me 3. 6 minus 2 gets me 4. Okay, so if I want to give you some arbitrary number of sides, 10 sides, 15 sides, 132 sides, I need to have a plan how to get these numbers. Well, if this number is always 2 less than this number, and I say this is n, this has to be, this part right here, okay, would be the n minus 2, and then times 180, because there's 180 degrees in one triangle. Okay, so quickly let's make sure we can put this formula into action. So let's find the sum of the interior angles in a 30-four-gon. Now what does that mean? Let's take a look at our formula. To calculate the sum, this is what I want over here. I need to know n. N is the number of sides. I have the number of sides. So all I have to do is take this 34 and plug it in for n. Okay, so plugging this 34 in for n, I get 34 minus 2, parentheses first. Let's think good Algebra 1 and PEMDAS. 34 minus 2 is 32. 32 times 180 gets me 5,760 degrees. So could I draw you a 30-four-gon? Heck no, but I could find the sum of its interior angles. Okay, so take a look. Same formula. Okay, same type of problem, but there is something different. This time I'm saying name the polygon that has a sum of its interior angles equal to 2,700. So I am not giving you the number of sides. That's not what this 2,700 is. This 2,700 now all of a sudden goes on this side. It is the sum. Okay, so look how I've done this. I've put the 2,700 on the left side, and now I have to solve this equation. I can solve this one of two ways. I can distribute the 180, which I think a lot of people in Algebra 1, that's how their Algebra 1 teacher would tell you to do it. Distribute the 180, add the 360 over, divide by 180. Okay, but that's not how I choose to do it. I choose to divide both sides right away by the 180. Divide, divide. Okay, after I divide, I get 2,700 divided by 180, I get 15, and I'm going to just now add this 2 over, and I'm done. Okay, so I've got n equals 17. Now don't forget it asked me to name the polygon. So how do I name something with 17 sides? I call it a 17-gon. Okay, had you distributed the 180 first, if you had distributed the 180, you would get the same answer. And maybe you want to pause the video right now and go ahead and try that. Distribute the 180, solve it that way, and make sure you do in fact still get that the answer is a 17-gon. Okay, so moving on, we need another formula. So the next one I want to talk about is, well, how do you find the sum of the exterior angles? Now, this one's going to take a little bit more work to get to the actual formula, but then when we get these numbers, I think the formula is going to pop really, really quickly for you. So let's talk about what is an exterior angle on a triangle first. Okay, so look what I did on the triangle with this black line. I have taken one side of the triangle and I have extended it out. Okay, that has created an exterior angle here. So the exterior angle is outside the triangle, but it's formed by taking one side and extending it past. So there's one exterior angle. Now, why did I choose to extend this side and not this side? It doesn't matter. I could extend either side. So if I extend it the other way, it would still be an exterior angle. I just happened to make this one at this vertex. Okay, I'm going to make an exterior angle at each of the 3 vertices. One angle per vertex. Okay, so exterior angle 1, exterior angle 2, exterior angle 3. One at each vertex, just like we talked about. Okay, go with me on this next part here. Okay, so here's what I know. If you see what I've circled a pair of supplementary angles. I know that a pair of supplementary angles add to 180 degrees. Now I have another pair of supplementary angles up there at that vertex, and I have a third pair of supplementary angles at that vertex. So 3 pairs of supplementary angles, 3 times 180. But that's not what I was asked to do. I was asked to find the exterior angles, so only the ones with the black markings on them. I don't want the whole supplementary angle because that includes the angle in a triangle. But the 3 angles in a triangle I know add to 180. So I can take these 3 groupings of 180 and I can subtract off 180. Okay, so 3 times 180 minus 180, if you do the math on that, you're going to get a sum of 360 degrees. Okay, fine. Maybe you're with me, maybe not quite yet. I'm going to repeat the same process for my parallelogram here. Okay, parallelogram, 4 vertices. I have one exterior angle at each. Maybe you're okay with me saying these two exterior angles are congruent and these two are congruent. Maybe you're not. That's kind of irrelevant. What is relevant, however, is that I have a pair of supplementary angles at that vertex, a pair of supplementary angles at that vertex, a pair of supplementary angles at that vertex, and a pair of supplementary angles at that vertex. So I have 1, 2, 3, 4 pairs of supplementary angles. But wait a minute, if I calculate this, that calculates the interior angles as well as the exterior angles. So I have to find a way to subtract off the interior angles. Good thing I know that the interior angles here add up to 360 degrees, or specifically, it's 2 times 180. Okay, so what am I saying? I'm saying that I've got 4 pairs of supplementary angles, one at each vertex. I'm going to subtract off the 360 for the inside angles of any quadrilateral. And if I compute this, okay, mathematically punch in your calculator, I'm going to get the sum of the exterior angles in a quadrilateral to also be 360. So maybe you're seeing, hey, 360, 360. I wonder if this one's going to be 360. So glad you asked. Okay, so I've removed a little clutter from the page, but look what I'm seeing. I'm seeing a pair of supplementary angles there, a pair of supplementary angles there, a pair of supplementary angles there, a pair of supplementary angles with a vertex there, and a pair of supplementary angles with a vertex there. So how many? I am seeing 5. 5 times 180, because again, supplementary angles add to 180, but just like every time before, I want to subtract off the inside parts. I only want the exterior angles. So if you remember, what do we know about a pentagon? I know how to find the sum of the interiors. The sum of the interiors would be 5 minus 2, which is 3 times 180. Okay, again, if you go through and you number crunch that, okay, 5 times 180 minus 3 times 180, what are you going to come up with? You're going to come up with 360 degrees. Okay, look at the pattern. This is 3 times 180, this is 1 times 180. The difference between them is 2. This is 4 times 180, this is 2 times 180. The difference between them is 2. This is 5 times 180, this is 3 times 180. The difference between them is 2. 2 times 180 is 360, 360, 360. What's the conclusion we're making? The sum of the exterior angles, 360. Okay, I just want to make sure you're with me. So find the sum of the exterior angles in a heptagon. Heptagon has 7 sides. Does that matter? Not really, because the sum of the exteriors is 360 degrees every single time. So heptagon, the sum of the exterior angles, 360 degrees. Okay, so find the sum of the exterior angles in a 1,275 gon. Easy, 360 degrees. Now I should make note that for this formula, for the sum of the exterior angles, I really can't ask you to go backwards. I can't say, hey, the sum of the exterior angles in a polygon is 360 degrees. What's its name? It could be any polygon out there, so really you can't go backwards with this formula. So what does it mean for a polygon to be called regular? Okay, if you have a regular polygon, your polygon must be both equilateral and equiangular. It must be both, not just one or the other, both. Okay, so look at the 2 different pentagons I drew. On the left, I definitely have a pentagon. It's got 1, 2, 3, 4, 5 sides. We know that the sum of the interior angles is 540, and look at how I've divvied them up. Right? Maybe I've got 2 that are the same, but the point is it's not equiangular. So if I want to take a pentagon and I want it to be equiangular, and that's probably the best I can get it, the sum is still 540, but what does each angle have to be if it has to be equiangular? So in order to figure that out, I have to take my sum of 540 and I have to divide it evenly by the 5 angles. So 540 divided by 5, that gets me 108, which means this angle is 108 degrees. This angle is 108 degrees. This angle is 108 degrees, 108 degrees, and 108 degrees. Okay, if I want this to be regular, I have to go ahead and mark the sides as well. So if I ask you for the sum of the angles in a regular pentagon, regular octagon, regular 27gon, you still find the sum the way we already talked about that. If I tell you it's regular, I can now ask you to find each angle. And we're going to use a little bit of division. Okay, so quick example. Let's find the measure of one, let me emphasize that, one interior angle in a regular decagon. So here's what we know. I could find the sum of all of the interior angles using this formula, but I don't want the sum. If it's regular, that means the sum has to be divided evenly amongst the 10 angles. So let me start by finding the sum. Okay, so remember, a decagon has 10 sides. If I take the 10, I plug it in. This is the 10 right here. The sum of the interior angles of my decagon, 10 minus 2 is 8. 8 times 180 is 1440. But I don't want the sum. It doesn't say find the sum of them. It says find one of them. So because my shape is regular, I can say now that each angle is the total 1440 and then divided by the 10 angles. So one interior angle is going to have the measure of 144 degrees. Okay, so last example. Thank you for staying with me until the end here. Okay, almost the same example as the one before, except I've changed interior to exterior. But again, look at, I'm asking for one exterior, and I am telling you that the shape is regular. Okay, so we know that the sum of the exterior angles in any polygon is always 360. Regular, not regular, 4 sides, 104 sides, doesn't matter. Okay, the sum of the exterior angles is always 360. But I don't want the sum. I want to know one angle. So what do I have to do? I have to take my sum and I have to divide it by how many angles I've got. So the sum of my exterior is 360 divided by 10. And I get that each exterior angle in a regular decagon, regular is the key, in a regular decagon, each exterior angle is 36 degrees. Okay, so to wrap it all up, thanks again for staying with me. Any polygon out there, 3 sides, 10 sides, 100 sides, you can find the sum of the interior angles by using the formula n minus 2 times 180. And you can find the sum of the exterior angles, it's just a fact, it's 360 degrees every time. Okay, if your polygon is regular, then you can take this sum and divide it by the number of sides to figure out the measure of each angle individually. And if you take the sum of 360 and divide it by the number of sides, hence the number of angles, you can find the measure of each exterior angle in your regular polygon. And there you have it, 4 key formulas for polygons.